We are given the graph of g of x, and we want to sketch the graph of y equals negative g of x. So we see that negative sign, and now we have to start to think, okay, what kind of reflection is this one going to be? Is this going to be a horizontal reflection, or is it going to be a vertical reflection? Well, that negative is outside of our function. Everything outside of our function is going to be vertical. It's going to affect our y values. So this case, we are going to reflect over the x-axis, because that's what a vertical reflection would do. And we can take some points. Again, this would be a key point, this one would be a key point, and reflect those over the x-axis. So where do they end up? Well, this one is 6 away, 2, 4, 6. This one is 2 away, 1 box away, which is there. And now that we have those two, maybe you can imagine where this graph is going to be. But I also want you to think, when I draw the blue graph, it is going to intersect the red graph at one particular point. Where is that point going to be, and why? So if I start drawing the blue graph, you can see right now it hasn't intersected anywhere yet, but as I go up here, it's going to intersect somewhere. Where is that blue graph going to intersect the red graph when I finish drawing it? This side is done. Where is it going to be? What's that point called? Close. You're right at the intercept. The y-intercept would be right here. Is it good? It's going to intersect there. Well, that point would get reflected down to there, but it will intersect right there at our x-intercept. Why does that happen? Why does it happen graphically? Why does it happen algebraically? These are the kind of thinking questions we want to be doing throughout the year, trying to understand why this is happening. And most of the times we'll be like, yeah, it makes total sense. Sometimes the why isn't as easy, but we need to think about those things. Graphically, if you reflect it over the x-axis, why doesn't an x-intercept change? It's already on the x-axis, right? If something's on there and you're flipping it over that, it's going to stay exactly at that same point that it is. Algebraically, why does that happen? Now, when I talk about algebraically is looking more at, like this point is at 3, 2, and our blue point on the image graph is at 3, -2. What has happened algebraically? What has changed? Our y-coordinate has changed, and our y-coordinate has been multiplied by -1. In fact, with any reflection over the x-axis, any vertical reflection, algebraically, that's what's happening. Our y-coordinates are being multiplied by a -1. So algebraically, if I think about an x-coordinate, so here's my x-coordinate on my red graph. It's x, 0. I don't know what that x value is. It looks like it's at about -0.2 or something. But my y-coordinate with an x-intercept is 0. What happens when I multiply my y-coordinate by -1? On my blue graph, my x value is not going to change. And what happens when you multiply 0 by a -1? It stays 0. So that's algebraically why it is when you reflect it vertically that your x-intercept doesn't change. And when we graph it, it makes a lot of sense flipping that over that that's the point that's not going to change. Now it says to state the domain and range of each function. In this one, our original function had a domain of everything and a range of everything. And reflecting that didn't change. Our domain and range are still everything. Had it been a different graph, that might have changed. But in this case, both our domain and range are everything. Questions for practice now? 4, 5, 6, 10, and 11.